Welcome back to the fourth part of steel beam design. In this video, we are going to understand about web crippling, web buckling, and also about what are the limits in terms of deflection as given by IAS 800 2007. So let's get started. So as you can see in this diagram, so this is the I section which is kind of failing in wave crippling, right? So why does it happen? It's because like when there is a concentrated load on a beam or at the support where a huge amount of load transfer is happening. So all of a sudden the load is transferred into the support, and if you see this bearing plate, the beam is resting on this bearing plate and all the load above it is being transferred to this portion only. So this actually imparts a huge force in this region, or rather I should say in the wave, which is primarily responsible of transferring the load to the support. So the wave cannot actually handle this load and it ultimately cripples, and by that way it fails by wave crippling. So we have to check our beam whether it is failing, it is susceptible to fail by means of wave crippling. So how can we do that? It's very simple. Say the base plate here is having a width B, and one thing we have to assume that the load is transferred in a slope of 1 is to 2.5. Like if I go one vertical up, it will go 2.5 horizontal. So that is how the slope is there, by which we assume that the load is distributed, right? So basically, at which height the wave crippling may occur? Basically, you see this portion is the flange width, and above that there is a dotted line, right? After some gap. Why is that gap? Because obviously you can see there is, when there is a flange and from there is a radius. So the width of the wave actually starts somewhat above the flange, right? Not exactly at the flange, somewhat above the flange due to this radius, due to this particular radius. Okay, so this amount of radius that is represented as R1 is given already. You'll find while looking for the section properties of the beam that you are using. So this amount is there. So basically you have to find this particular length on which you have to support that particular the load that is coming onto the beam and to the base plate that is being transferred. So the total length becomes B plus N1, where N1 is, you can say, 2.5 times TF plus R1. That is, this is the vertical distance that you are traveling upward. So if you convert it into horizontal, like from here to here, it becomes 2.5 TF plus R1. This is the N1. So this multiplied with the thickness, you will get the area available, right? So that is how you can, that area will be carrying the load that is being transferred here. So ultimately that area should not fail. You have to make sure that. So that is how you can check for wave crippling. So when we do our problem, you'll see how it's gonna pan out. And there is also another thing. This is wave, we just discussed wave crippling. We also have another thing called wave buckling. So how does it look? It kind of looks like this. So it's kind of a buckling, and which is happening to waves. So this happens because there is a huge amount of uh, vertical load that is on the beam, and due to the huge amount of shear force, the wave, which is rather very thin, it tends to buckle and ultimately it fails under buckling. So interestingly, we usually don't check for wave buckling if my ratio d by tw, that is d is the depth of the wave and tw is thickness of the wave, d by tw, if it is less than 67 epsilon, right? 67 epsilon, epsilon is root over 250 by fy. If it is less than 67 epsilon, then in that case we don't check for wave buckling. We assume that it is safe, right? But in case it is greater than that value, ultimately we have to check for shear wave buckling, right? So that's that. So we already discussed wave crippling and wave buckling, and last thing we are gonna do is check for deflection limits, right? So in page 31 of IS 800, page number 31 IS 800, you will find table 6, where deflection limits are specified for different kind of members, right? Different kind of members. So if you say can take any value, like for live load of a simple span, what should be the, say for, we take for brittle cladding, span by 300, right? So it varies from case to case. So for other buildings apart from industrial buildings, for vertical floor and roof, there is span by 300, span by 360. So it's just that you have to take from case to case, whatever your situation is you have to take accordingly. In general, when we are doing normal beam problem for house, maybe uh, steel beam designing, we usually take span by 300. And the problem that we'll be doing in later videos, we'll actually see we have taken the deflection limit at span by 300. So in the next video, we'll see how, what are the different steps that we need to do while designing a beam. So far now we have like covered everything in bits and pieces. Now it's time to take it together and make a whole problem, or make a overall process of how to design a beam.